and would say go ahead.
All right, let's get started then. Good afternoon, everyone. Don't you love an introduction to an introduction? But here we go. I'm Tim Wagner, and I'm a researcher here at SSCC and a frequent instructor in the Atmospheric and Oceanic Science Department. And I'm here to introduce David Loveless in his presentation today. David and I have been working together for since I arrived at SSCC back in 2015. David's been here since 2014, I believe. He got his undergraduate degree from SUNY Oneonta. It's the same program that Steve Ackerman went to so long ago. But he came here and started doing research on a bunch of ground-based remote sensing problems. Early on in his career, he was a significant participant in the Pecan Field Campaign, in which he and I and a bunch of other people drove many thousands of miles around the Great Plains looking for severe storms and tracking how those environments were changing. His master's thesis was written on using ground-based instrumentation to assess how the atmosphere is changing during atmospheric bores. Some really cool stuff that we got out of that. And since he finished his master's, he and I have been working on a PhD project, officially under the supervision of Steve Ackerman, on how can we use ground-based and satellite instruments together, one pointing up, one pointing down. How can we join them together in order to have better retrievals than we could if we just did those things separately? And so, of course, David is going to tell you a whole lot more about that now. I will say it's been great working with him all these years, and he's done some really cool work. And I think you'll be interested in the results that he has to show. So with that, I will cede the floor to David. Take it over.
All right, thank you, Tim. I'm going to, let's see here. Should have had this ready before. I'm going to share screen. Okay, and if I could. Okay, does everyone see my presentation now?
Yep, looks great.
Okay, sounds good. All right, so thank you, Tim and Pete, for putting this together and manning the technology. So yeah, I'll be talking about how we're looking at potentially using ground-based instruments to improve observations of the planetary boundary layer. Before I start, I'm going to note, please feel free to interrupt me if you have any questions. It gets really weird talking to an empty room, so I'll appreciate feedback if you have any questions. So with that being said, I thought I'd start off with some context for this work in noting the current sources of thermodynamic profiling in the operational observing system. So we have radiosondes, which are kind of the gold standard. However, they're only launched every 12 hours and kind of on this very coarse grid. Aircraft do take temperature and moisture observations throughout flights, and you can get some form of profiling capabilities during takeoff and landing. And then the majority of the sounding observations come from space-based profiling from IR and microwave instruments. You have two distinct constellations of polar orbiting satellites from the US and from Europe. China recently launched a geostationary sounder called GEARS, and EUMETSAT has plans to launch one as well in the future. And then you also have radio occultation observations, kind of providing observations kind of pseudo-random in space and time. So really the motivation for this study comes from two government reports, the National Research Council first in 2009, and then on a larger scale, the Decadal Survey in 2017, highlighting that space-based sounding of the planetary boundary layer is currently inadequate in accuracy and resolution for the purposes of numerical weather prediction and nowcasting and general monitoring of severe weather environments. So to gain a bit of perspective of how bad we're talking, so this is NUCAPS is the NOAA operational retrieval for the polar orbiting satellites, CRIS and EASI. And so you'll note that generally these comparisons with radiosondes are within about 2 degrees Celsius throughout the entire profile, and then you get these really large errors near the surface. Their microwave figure here, the water vapor figure here, water vapor mixing ratio, looks at a percent difference. So these 10 to 20% differences near the surface are probably like 2 to 3 grams per kilogram errors. And essentially, these reports are saying this is not good enough for what we need right now. And basically, the Decadal Survey says we want to invest money in this moving forward to fix this problem. While the National Research Council actually suggested the development of a nationwide network of thermodynamic profilers on the ground. And so that's kind of where we get this idea from, is this report that basically says, let's supplement space-based sounding with ground-based sounders. So just a quick overview on the concept of how the idea of infrared sounding. You basically, the blue line here would be what a space-based sensor would observe, while the green line would be what a ground-based sensor would observe. You'll note that these radiances are very different in their characteristics. With window channel here, you're looking at essentially the surface temperature from the space-based instrument, whereas in the window, you're looking almost at background space radiation. And then if I overlay a couple well-known, absorption bands, you could basically use radiances in these bands from carbon dioxide, ozone, and some other trace gases to kind of back out temperature profiles. Excuse me. And so just how much better are these ground-based sensors at sensing in the boundary layer? So this is a study, basically, excuse me. So this black line here is a radiosonde profile, whereas the blue line is a space-based retrieval, and the red line would be the AERI retrieval, which is a ground-based sensor. And so you could see that in this case, the AERI does a really good job of identifying the low-level inversion that the space-based retrieval just cannot observe. And then similarly, when you look at water vapor, the AERI is much closer to reality than the satellite is. And then you'll note that once we get to the top of the boundary layer, the satellite's much better than the AERI is when you get into the free troposphere. So this is just another way of looking at it. The differences here compared to the radiosonde display that two different kind of modes of the boundary layer, where the AERI is much better than the satellite sensor, and then the free troposphere, where the satellite sensor is much better than the AERI. And so one of the studies that kind of suggests that this ground-based and space-based combination is promising is work from Jessica Gartsky here. Basically, she compared CAPE calculations from AERS retrievals with CAPE calculations from radiosonde profiles. And you could see here that there's essentially no correlation between the two. It's just simply adding the surface observation to the bottom of the AERS retrieval, that correlation is significantly better, which kind of gives credence to, yeah, we're missing the surface, near surface characteristics with these satellite measurements. Then there's also this study from Kirsten Ebel over in Germany that she basically used a ground-based microwave radiometer and compared it with different combinations of AERI and the whole suite of space-based sensors that UMetSat has. But the main piece that so this figure here is basically showing the synergy benefit. So how much, say, microwave plus EASI is compared to using the ground-based microwave sensor alone. And so what I want to kind of highlight here is when they added EASI to this ground-based ground-based microwave radiometer, they still improved information content within this surface to 800 millibar layer, despite the microwave being on the ground. The space-based instrument still provides information near the surface, and so this kind of brings us to this point that a synergy is a synergy, or a combined retrieval is better than some form of combination of the retrievals, running the retrievals separately and then trying to piece them together based on where they're typically more accurate. So what I want to ask here in this study that I'm going to do is, what are the improvements when we add a ground-based sensor to a retrieval with a space-based sensor? Going back to here, I should note that she's basically quantifying these gains compared to a microwave radiometer alone. However, we have a whole bunch of satellite instruments and we don't have an operational network of ground-based instruments. So let's reverse the question and quantify the improvements when we add a ground-based sensor compared to a situation with only the space-based sensor. And so in order to do that, we'll look at 3 pieces of information: degrees of freedom, vertical resolution, and the uncertainties of this theoretical retrieval. And then, since we want this solution to work in multiple climate regimes, we'll also ask the question of, how does this information content change with varying water vapor concentrations? And so in order to answer that question, I'll consider 3 stations in different climate regimes. So the atmospheric profiles I'll use as input to this synthetic study will be from 3 different ARM stations across the northern hemisphere. Basically, we have the Southern Great Plains site in central Oklahoma. We have the East North Atlantic station at the Azores Islands, and then the North Slope of Alaska. So 3 very distinct climate regimes here. Basically, we'll grab a bunch of radiosonde profiles as input to our model, and we'll do some cloud clearing. So basically identify every radiosonde with relative humidity greater than 90% and say that that's a cloud and screen those out. And what you're left with is about a little less than 500 profiles at the Azores and North Slope of Alaska, and then more than 3,000 at Southern Great Plains site. This is a product of both there just being more clouds in the Azores and North Slope of Alaska, and also Lamont, or the Southern Great Plains site, has more intermediate time radiosondes, so 6Z and 18Z radiosondes. So there's a larger pool to pull from here too. So the instrumentation I'll consider, basically AERI will be our ground-based sensor, and then AIRS, CRIS, and EASI are kind of the traditional polar orbiter polar sounders that NOAA and UMETSAT fly. I'll include ABI in our analysis because it is geostationary, and that adds an important component to temporal component to observing weather in the US. So it is an imager, so it has much less information. And I'll add the GEARS geostationary sounder that China recently launched. Since GEARS has kind of high noise, a conversation with Bob Knutson led me to using this GIFS sensor noise, which is basically a sensor that was proposed by some people here at SSEC. Basically has well understood noise characteristics. It was supposed to be a geostationary IR sounder as well. So we basically used the GEARS channels with the noise characteristics of this proposed instrument to kind of make it more realistic. And so roughly, what do we do with all this information if you don't know much about sounding? In general, the ABI, being an imager, has broadband channels, and so it shouldn't have much information for sounding purposes. AERS, CRIS, and EASI are very similar. EASI has slightly better spectral resolution, while CRIS has better noise. AERS is older and has higher noise than the other two, but has a longer data record. So there's kind of these trade-offs between the different sensors there. And so the radiative transfer modeling will put these profiles into, we'll use a fast model called OSS. It's a line-by-line model, but it's essentially a lookup table derived from LBL-RTM. And this basically makes it practical to run our analysis over a large number of profiles. We'll use trace gas, consider absorption and emission from trace gas from carbon dioxide, nitrous oxide, ozone, and methane in our modeling, and then we'll keep these four constant for all of our profiles and allow water vapor to change with those radiosonde profiles we use as input. We'll use the CAMEL emissivity monthly climatology for each site to as an input, and then we run our calculations on the AERS 101 pressure levels. Since it's the grid's very strongly used in the satellite community, and so we kind of want to meet them at that. But I will note that we've found that this degrades the information that the AERI provides a bit, so it kind of underestimates the AERI. And so to start off with, the first thing we'll look at is degrees of freedom. To calculate that, you need a priori covariance matrix. Basically, this is computed from clear sky profiles from each station. So we use the same number of profiles from each station and from each season at each station. So kind of develop this pseudo global prior, if you would. And then you can calculate an averaging kernel using basically that prior. If we use instrument noise for this SE here, and then the model will use the radiative transfer model to calculate K, your Jacobian, which is essentially the change in radiance with, say, change in temperature or change in water vapor. And so the averaging kernel will be a height by height matrix, and the trace of A will tell you the degrees of freedom, which is the number of independent pieces of information, is essentially how you could think of that. So before I show some results from this, I'll note that because we're only using the instrument noise for the error covariance matrix, we'll kind of overestimate the information. We'd go with this though because model errors are difficult to account for. And then second, we're not accounting for the spatial variations in temperature and water vapor that space-based sensors will be sensitive to, since they have about 15 kilometer sized 15 square kilometer footprint. And then also I'll note that this method is basically assuming that we know the skin temperature and surface emissivity, whereas an ideal retrieval would likely retrieve those quantities at the same time as retrieving temperature and moisture profiles. So when we calculate degrees of freedom for all of the profiles at the Southern Great Plains site, I'll use this surface to 700 hectopascal layer as a proxy for the planetary boundary layer. Essentially what we're looking at is the black boxes here are basically the respective instruments alone, and then the red is basically ABI with the AERI, AERS with the AERI, CRIS with the AERI, etc. And so you can see that AERI on its own has much more information than all of the space-based instruments by themselves. You can see that ABI doesn't really provide much information at all. When you add the AERI to the retrieval with any of these space-based sensors, there's a significant improvement. And most notably with the sensors that are designed for sounding, you'll end up with approximately a 1.5 degree of freedom increase in information, regardless the type of regardless the sensor. The other thing I'll note is, it was kind of interesting to find, is that AERS, CRIS, and EASI are all very similar in their information content, which is not exactly what would have expected, but I've heard from conversations with other people that others have been finding that as well, which kind of is an important finding when you consider the planning for future sensors in the observing system, essentially. Basically, these are all kind of different instruments, but we're still ending up at roughly the same information content. And so looking at the North Atlantic now, you see a very similar pattern. This is still for temperature. You see a very similar pattern with about a 1.5 degree of freedom increase. And then in the North Slope of Alaska, again, very similar increase for that the AERI provides. When we look at water vapor, that improvement that the AERI provides is slightly smaller. It's a little less than 1.5 degrees of freedom, but more or less still seeing the same pattern. Once again, AERS, CRIS, and EASI are very similar. ABI has essentially no information. GEARS has a little bit less information, but again, it's a geostationary sensor, so that would be to add the temporal component, which is important that the polar orbiters would not pick up on. And so if I just click through the rest of the other two stations here, it's essentially the same pattern, though we do see subtle differences across the stations. So basically a quick summary of where we're at right now. There's roughly a 1.5 degree of freedom increase or improvement that the AERI provides compared to one of the hyperspectral sensors alone. And then when you think about water vapor, it's about 1 degree of freedom increase. And so there's these subtle differences across the stations. So I want to ask, is there a relationship with moisture here? And so what we could do is look at basically bin this, so we have all these profiles with varying precipitable water across all the different stations. So I basically bin up, say, all the profiles from 0 to 1 centimeters of precipitable water vapor. And this is the information content that we get, and so on. And so we see that there's a little bit less information in dry environments from the CRIS perspective for the full troposphere than there is in more moist environments. So kind of as you get as water vapor increases, you increase information content. And then the very moist cases, I'm not sure what, I wouldn't bank on this conclusion here because there's not a whole lot of cases in the 4 to 5 centimeter, 4+ centimeter precipitable water vapor bin. So I'd kind of be skeptical of that. It's this U shape and not just a general arc there, kind of leveling off. But anyway, so if we look at CRIS with the AERI, so the synergy, you see the same pattern. So I want to ask, is this pattern with water vapor? And the answer to that is no. Basically, if we look at information content for water vapor, there's really no signal at all when it comes to changes in water vapor information content with changes in precipitable water vapor. Does this pattern happen near the surface, though? And that answer is also no, and that's regardless of whether or not you use the synergy or not. Perhaps you have a very slight difference here of about 0.5 between this peak in information at 2 to 3 centimeters and the 0 to 1 centimeter bin, but it's really not much of a difference. And so if I just keep the CRIS perspective here and look at AERI, AERI does not have a pattern on its own either. So this is basically just CRIS differences that CRIS identified, or sorry, differences in CRIS information content with precipitable water. And I'm not real sure why this is the case. This is kind of found this with AERS and EASI as well, not just CRIS. And so I'm not sure what causes the space-based sensor to be sensitive to differences in water vapor concentrations, whereas the ground-based sensor is not. So that's kind of an open question that I'm looking to solve, hopefully in the next month or so moving forward. So looking at the second piece that we want to look at now is vertical resolution. And so just to clarify what I mean by vertical resolution, I'm not referring to the resolution of the vertical grid that we do calculations on, but rather when you do sounding, infrared sounding like this, there's a particular thickness of the atmosphere that is contributing signal to the retrieval when it makes an estimate at a particular point. So what I mean is, if let's say there's a vertical resolution of 1,000 meters, what that's saying is when the retrieval estimates the temperature and water vapor at that point, it means that it's receiving signal from across 1,000-meter slab of atmosphere when it makes that estimate. And so obviously the thinner that slab is, the smaller the smaller that quantity is, the better your estimate. The more you can identify the, say, the sharp gradient in water vapor at the top of the boundary layer. And so there's kind of two different ways you can calculate this. They're kind of similar. First method is calculating the full width at half max of the rows of the averaging kernel. Or you could essentially, this guy Hewison made this approximation where you spread the information from the diagonal elements of the averaging kernel across the vertical spacing of the grid. So that's what we're going to go with, is basically this approximation for vertical resolution. And I'll note that degrees of freedom was the trace of A. So we're basically, again, utilizing the diagonal elements of the averaging kernel to determine our vertical resolution. So there's a direct correlation here between degrees of freedom and vertical resolution. And so once again, I'll recall that our caveats to the methodology that we used is likely to overestimate vertical resolution, given that we basically assume, kind of remove a lot of sources of error and uncertainty from our analysis, model errors and spatial variability from the satellite side. But with that being noted, we can look at these profiles of vertical resolution for the different sensors. So AERI is going to be in green here, CRIS will be in blue, and then the Synergy will be in this gray shading. And so what we're looking at is one line is the 25th percentile, and then the other side is the 75th percentile, and shading between that. And so first of all, what we see here is that AERI, as one would expect, has much greater vertical resolution, has superior vertical resolution. I shouldn't say greater, has superior vertical resolution near the surface. I'll note that AERI's resolution is basically being limited down here by the vertical grid we're using. We're using a satellite-based grid, and so it's very coarse. Whereas if you look at vertical resolution using like the native grid that AERI-OE, the AERI retrieval uses, you'd have much greater information content very close to the surface. So I'll kind of note that we're being limited down here. But beyond that, there's a lot of interesting stuff that you could see with a figure like this. Notably, you could see how the Synergy starts utilizing information from both sensors, as basically from about 500 meters up to about 3,000 or 4,000, it's better than using either AERI or CRIS alone. And so you could basically see how the two different views of information are kind of working together to improve the retrieval in this top of the boundary layer, bottom of the free troposphere area. So I'll note that the Decadal Survey kind of set a 1 kilometer vertical resolution goal. I'll recall our caveats again to our methodology, probably overestimating vertical resolution, especially from the satellite side. We're not really reaching that 1 kilometer goal here, but there is dramatic improvement in in kind of the bottom 1,000 or bottom 2,000 meters of the atmosphere, though.
David, what causes that knee at the low levels in the gray in the combined retrieval?
Some of the, there's some noise, like some of the, there's likely a couple outliers here that are basically throwing off the averaging, if you would.
Okay.
Yeah, is there any other questions?
Yeah, no, that makes sense as you describe
Okay,
it.
yeah, there's some profiles that just look really funny, and so some of them start throwing off figures like this. Yeah. So if we look at the vertical resolution for water vapor, overall it's a pretty similar pattern. We're again not really meeting this Decadal survey goal, but we are about roughly doubling our resolution near the surface. And again, this really cool looking, at least to me, it's really awesome looking how the retrieval basically uses information from both sensors at the same to be better than using one sensor alone. And so you could really see that really well in that kind of upper boundary layer, lower free troposphere region. All right, so moving on to the third aspect of the study, uncertainties. So I'll once again bring back the averaging kernel. I'll note that this quantity here is called the posterior error covariance matrix. So essentially, we can use that to create these quantities known as 1 sigma uncertainties. So you think of it like about 68% of the time your uncertainty should be within this plus or minus this quantity roughly. And so we'll make the same sort of profile figures as we looked at for vertical resolution. And we again see that there's dramatic improvements that the AERI brings dramatic improvements to this type of retrieval compared to the space-based retrieval on it, space-based sensor alone. When you add the AERI, and so again, you can see how the synergy utilizes information from both instruments, thus again kind of hammering home this point that the combined retrieval is much better than using two instruments retrieving, say, running the well-known AERI retrieval and running the well-known like NuCAPS retrieval on CRIS, and kind of trying to mash them together. Then you're much better running a combined retrieval. And so let's again look at the Decadal survey targets. So that's 0.3 to 1 Kelvin uncertainties. So we are less than 1 Kelvin all the way up in this. However, is that realistic? Well, I'll bring back this figure that we looked at earlier, and kind of note that CRIS, our shading for CRIS here, is kind of overdoing how good CRIS is. My synthetic study has about is about at 0.5 Kelvin throughout most of the troposphere, whereas a radiosonde validation will be something closer to 1.5 to 2 Kelvin. So my analysis is kind of overestimating how good CRIS is. Let's think of, we could also look at how my analysis is doing for AERI alone, and we find that it's roughly in the ballpark compared to what radiosonde validations have shown. But again, with CRIS kind of being overestimated, the synergy in the free troposphere is likely being overestimated as well, where it's basically completely depending on CRIS. It's probably being overestimated. So we do something similar for water vapor again. And once again, you see that AERI has dramatic improvements near the surface. We have this weird pattern. You can kind of see where the top of the boundary layer tends to appear in most of my profiles. And so we could, again, compare to the AERI, this validation study for the AERI. We're in this case overestimating how good the AERI is this time on the water vapor side. The bias is, the RMSE is about 1 gram per kilogram that Dave Turner's finding, whereas we're finding much less than that, so we're overestimating the AERI. If we convert this figure to percent differences of water vapor, we can make a comparison back to that NewCap study, and we see that this time the CRIS errors are roughly ballpark what a radiosonde validation study has found for CRIS or Yazzie water vapor uncertainties. So we're kind of overestimating how good the AERI is in this case, and underestimating how good CRIS is aloft. Or sorry, we are on target for how good CRIS is aloft, and overestimating how good the AERI is below. So before I wrap up here, I just want to kind of note that there's some open questions about the idea of this ground-based network. Putting ground-based sensors across the country would not solve the PBL sounding problem over the ocean, and thus you wouldn't really see improvements to medium-range forecasts. However, a ground-based network would provide very strong improvements to 1 to 3 day forecasting in the US, in addition to providing a very useful tool for nowcasting, given that the AERI is basically able to make provide thermodynamic soundings at a more or less continuous continuous basis. So you could see rapid changes in the environment with the AERI. And so this kind of space-based, ground-based matchup works best with a geostationary instrument, basically providing you continuous views from top and bottom. However, in the US at least, we don't have a geostationary sounding instrument, and we don't have a ground-based network either, so there's a lot of cost involved in that. And then there's also the question of how many locations and where would these profilers go on the ground. So conclusions here is basically that AERI adds significant information in the near surface layer compared to what we are currently getting from the space-based infrared sounding that is currently available. Again, the geostationary sensor is kind of the best matchup for this, which is kind of lacking in the US at the moment. And then I'll note here that uncertainties that we've estimated differ from results that have been found in radiosonde validation studies, but you can still get a sense of the significant improvements that the AERI would offer. And then I'll also note that we saw the significant improvements that AERI makes in vertical resolution near the surface. And so some questions that we want to look at in the future moving forward here is trying to explain the changes in information that I showed with changing precipitable water vapor. And then we want to expand this to cloudy sky scenes. And since in theory, a ground-based sensor and a space-based sensor should be able to provide you information below the cloud and above the cloud. So that should be, the solution should work well in cloudy sky environments, which is typically a problem for infrared sounding. And then eventually we want to move to actually getting a real retrieval working on real data and compare it to radiosondes and see when we put this in motion, how good is it versus these synthetic studies. So I hope that everyone learned something, and I'll leave this on my conclusion slide and take any questions.
Dave, this is Paul Menzel.
Hi, Paul.
I wasn't clear on whether you're using the full CRIS spectrum or you're just using the 300 selected channels that NCEP uses.
Yes, so I am using all of the channels on all the sensors in this study.
Good, thank you. That's the right answer.
And then the counterpart to that is you must use all the channels on the AERI.
Yes, yes. Are there any questions in the chat? That window isn't showing up for me.
I haven't seen any questions. It's mostly clapping.
Okay.
What's going to be your approach with the cloud? That seems like a ton more work to do.
Yeah, so we use Dave Turner's LBL die sort model, which basically uses LBL RTM and then simulated in like a clear sky environment, and then you toss it those radiances and optical depths for the various layers, and Dave's addition to it basically computes the scattering part of the cloud. And so we have that working. It's just kind of getting Jacobians to look realistic right now before going through with doing essentially the same analysis just on some cloudy sky profiles.
Dave, do you anticipate that if you were to combine a microwave radiometer in addition to the AERI, would that add any additional information, or would it be pretty much redundant?
Are you thinking of a microwave radiometer in space or on the ground?
On the ground.
Okay, so let's see here. If I scroll back to, so if I go back to this Kirsten Ebel's study, basically this figure here is showing what a microwave radiometer plus the AERI would see compared to basically that synergy minus the information content that the microwave alone saw. So AERI plus the microwave provides new information, but I'm not sure about if you did the AERI, if you say subtracted whatever their quantity here was minus the AERI. I don't have that figure. I'm sure the answer is in there, and I'm not remembering off the top of my head. Yeah. This study though has that answer to your question. I just didn't screenshot the particular figure I need to show you, and I don't remember the answer off the top of my head.
Great, thanks. I'll take a look at it.
Yeah, I'm sorry about that.
How much would a LiDAR profile of the visible optical depth do for your cloud retrieval case?
For a cloudy sky case, you're saying?
Yes, to look at the cloud altitude and the optical depth up to about optical depth 3 or so.
Yeah, I'm not sure. So I haven't made much headway yet in cloudy sky analysis, and I haven't looked at LiDARs. And I'm not very familiar with LiDARs either. So I'm not sure, unfortunately, is my answer. I'd imagine that LiDAR would be pretty good, but I'm not sure.
It certainly give you the altitude of the clouds.
Mm-hmm. Which should help in the being able to reduce some of those variables that you'd be running your radiative transfer model on.
It would certainly limit the number of degrees of freedom in your cloud properties in the retrieval for sure with good accuracy.
Mm-hmm. Mm-hmm. I believe Dave Turner, when he runs AERI-OE, he inputs a outside source of cloud base height. Tim could correct me if I'm wrong on that. I believe that Dave Turner in
No,
cloudy
you're
sky.
right.
Go ahead. Whoever's talking.
Yeah, we include the cloud base from a co-located ceilometer for the most part. We're doing some work on can we get some basic height information just from the spectrum itself so that we can do it standing on its own. But for now, we tend to focus just on the ceilometer. Either we've got something co-located, or we tend to run this in tandem with a Doppler LiDAR. And so we'll use the backscatter from the Doppler LiDAR to help us indicate where cloud base is.
Any other questions?
Can you estimate or say something about the effect of the very different fields of view that you have from an up-looking AERI and a down-looking CRIS, let's say?
Yeah. So I kind of so when I did these simulations, I assumed that AERS, CRIS, and EASI were making direct like nadir overpasses over the AERI, so I didn't run them at scanning angles. And then I'm also assuming that there's just no horizontal variability across the footprint of, say, CRIS. So I'm kind of ignoring all that. I'm not some conversations with Bob Knudsen and Dave Turner, kind of not sure how to include that into our uncertainty analysis in an easy way. So yeah, I'm not sure what that effect is, but obviously it's going to add uncertainty to the retrieval.
Yeah, the way to maybe poke at it would be to have an AERI over the ocean looking up and compare with these land-based AERIs. It's a tough deal.
Mm-hmm.
It's a very nice presentation, David. Nice work.
Thank you very much, Paul. Any other questions?
All right. Thanks again, David.
Yeah, thank you.